All right, we'll continue to talk about Lewis structures. And we passed this slide previously. So electrons can be stabilized by bond formation. And then for part of the periodic table, this octet rule, the fact that they'll have 8 electrons around them in any good Lewis structure, is very strict. For carbon through fluorine, the octet rule is very strict. But for other atoms, it gets more complicated. Let's get into those more complicated cases then. The octet rule is a preference even for these others, but they do have some ways to get away with having either less or more than 8 electrons. So atoms in the beryllium group may have 4, 6, or 8 electrons around them. Atoms in the boron group may have 6 or 8. Heavy atoms, those heavier than silicon in the p block, may have 6, 8, 10, or 12 electrons around them. So let's look at some of these situations. So first is this so-called incomplete octet. So beryllium and the boron group atoms can be surrounded by less than 8 electrons in a structure. And so for example, we have a structure like this. BF3 is a boron connected to 3 fluorine atoms. And since it's only connected to 3 fluorine atoms, we have 6 valence electrons to deal with. For a variety of reasons, we can't, in these structures, form a double bond to the boron. And so that's just all we got to work with, is 6 electrons for this boron atom in the structure. This does end up meaning that this is very reactive. So if we show this, for example, a fluoride anion, it will react immediately. So it is very hungry for another pair of electrons. And then we have our expanded octet. So we have more than 8 electrons around. And so elements in column 3 and beyond have empty d orbitals that can be used in bonding. And so, for example, SF4 here, it has to have somewhere to put all of its electrons. It forms 4 bonds, and then there's 2 electrons left once we've formed all of our bonds and satisfied all our fluorines. Those 2 extra electrons go on sulfur, and that means this sulfur has to deal with 2, 4, 6, 8, 10 electrons around it. And yeah, it does it. Same deal here with PF5. This larger atom, it has 2, 4, 6, 8, 10 electrons around the phosphorus, and that's okay since it's a heavier atom, and it's okay for it to have this so-called expanded octet. And then I sort of swore to you that for carbon, nitrogen, oxygen, and fluorine, that they must stick to the octet rule, but there's a few cases where they just cannot manage it. And it's these cases here. And it ends up just being a mathematical situation. So nitrogen brings in 5 electrons, each oxygen brings in 6, so you have 17 electrons for NO2. And since you have 17 electrons, there's no possible way to simultaneously satisfy all of the atoms, because an octet is 8. 8 is even, and so any combination of evens would be even, and so how are you going to satisfy an even count with an odd number? So it just does not work out. Same deal here with NO. 5 from nitrogen, 6 from oxygen, 11 total. They would prefer to have an even count, but they just can't manage it because there's an odd total. Again, anytime we have these situations where we have an exception, though, both of these are extremely reactive. Both of these actually, if you actually have the chemicals, will dimerize and will satisfy the octet on the nitrogen in that way by dimerizing. So NO and NO2 both will dimerize, and both of these are very easy to either add an electron to or remove an electron from. And so that all comes from the fact that doing any of those will make their electron count on the nitrogen, will make it able to have an octet, because if we add an electron or remove an electron, we'll then have an even electron count. So here's all these together. So incomplete octet, so something that is in either the beryllium or boron column, can get away with having 6 electrons, or 4 in the case of beryllium. Expanded octet can get away with having more than 8. So it can have 8, 10, or 12 electrons around the central atom. And then we also have odd electron molecules. We have an odd number of electrons total. There's no way that each atom in the structure can have an even number. And so it's just the way it is. So sternness of the octet rule. The octet rule is really stern up here, with the exception of those odd electron molecules. Anything else is going to have an octet on carbon, nitrogen, oxygen, or fluorine. And the octet rule gets weaker as we go down. So when we get to these really heavy atoms, we have lots of exceptions where we have 10 and 12 electrons around the central atom. Okay, so let's summarize. All main group elements will try to obey the octet rule. This could be trying by moving their electrons around to achieve it, or by being very reactive if they don't. If we have a central beryllium or central boron group atom, it can have less than 8 electrons in a good Lewis structure. Molecules with an odd number of electrons, such as NO, will have 7 on one of the atoms, one or the other. Heavy central atoms, row 3 and beyond, can have more than 8 electrons around the central atom. The octet rule progressively becomes less strict as you move toward the heavier elements.